Welcome back, focused learners. Today, we're throwing on our detective hats and heading straight out into the field of plant construction. We're going to solve a serious mechanical mystery. How do we save massive, incredibly heavy rotating equipment from literally vibrating itself to destruction? Well, we're zeroing in on one absolutely crucial phase of installation. It's called the alignment inspection.
Seriously, think about it. Why do seemingly perfect, brand new pieces of rotating equipment, like these massive industrial pumps and motors, get completely destroyed right after they're turned on? Well, the answer is vibration, and the prime suspect causing all that shaking. It's usually a microscopic flaw that sneaks in during the physical installation of the machinery. To catch it, we rely on a process that might sound mundane, but it's absolutely critical.
So, here's our inspection roadmap to track down and eliminate that main culprit, which is misalignment. We're going to investigate Pillar 1, shaft alignment, Pillar 2, DBSE, and finally, Pillar 3, the very deceptive soft foot. Let's get right into it.
Take a look at this. It's basically our master key. This is the official alignment inspection sheet that engineers actually use out in the field. Notice how it perfectly maps out our entire three-part investigation. You've got the shaft alignment readings, the DBSE measurements, and the soft foot tracking. The final sign-off on a sheet exactly like this literally guarantees the lifespan of the machinery. Pretty cool, right?
Okay, let's start with our first major check. Pillar 1, shaft alignment. So, checking the shaft alignment is arguably the single most crucial activity if you want to extend your equipment's lifespan. Our prime suspect here is misalignment. This happens when the center lines of two connected shafts just don't perfectly coincide. They might be offset vertically, horizontally, or maybe sitting at a weird angle. And here's the crazy part. Even a microscopic deviation acts as a completely destructive, invisible force the second that machine spins up to thousands of revolutions per minute.
To catch those tiny microscopic deviations, we bring in highly skilled technicians known as millwrights. Whether they're using a modern digitized setup or attaching a traditional dial gauge straight to the shaft, the whole process is incredibly delicate. The millwright rotates the shaft a full 360 degrees to measure exact deviations. If someone unskilled tries to do this, they might fix the left side only to throw the right side completely out of whack. Seriously, you could spend all day on a single pump if you don't know what you're doing.
Moving right along, let's hit Pillar 2, DBSE.
Now, even if the shafts are perfectly aligned right down their center lines, they still need to be spaced correctly end to end. That's where DBSE comes in, which stands for distance between shaft end. If you're new to this, just think of it as measuring the gap between two mechanical components. It's the exact required spacing between the tip of the pump shaft and the tip of the motor shaft, exactly as the original engineering drawings demand.
Think of it like trying to park your car exactly 1 meter away from a wall just so you have enough room to open your trunk. If that DBSE dimension is wrong, the coupling mechanism that physically links the two shafts simply won't fit. Technicians use highly specialized tools to measure this gap, and if it's off, well, they literally have to use heavy-duty jack bolts to physically shift these massive motors until the gap perfectly matches the blueprint.
All right, that brings us to Pillar 3. This is our third and honestly, perhaps the most deceptive suspect in all of equipment installation, the soft foot.
To really picture a soft foot, imagine a wobbly restaurant table. You know the kind, right? Where one leg is just a fraction of a millimeter shorter than the rest, so the whole table rocks back and forth. Now imagine taking giant, heavy bolts and violently forcing that short leg down into the concrete floor. Sure, the table stops wobbling, but the entire frame is now under massive internal tension. That is exactly what happens when a motor has a soft foot. It looks completely stable because it's bolted down tightly, but it's artificially forced flat. That creates severe internal stress that will instantly turn into aggressive, damaging vibration the second the motor turns on.
So how exactly do our detective millwrights investigate this hidden tension? Well, they use a very specific step-by-step physical procedure. First, they tighten all 4 motor foot bolts completely down. Second, they loosen just one bolt. Just one! Third, they watch a highly sensitive dial gauge placed right on that specific foot to see if it springs upward. And finally, they tighten it back down and repeat that exact process for all the remaining feet, one by one. Out in the field, this is exactly what the hunt for a soft foot looks like. The technician carefully works the wrench to loosen a single bolt, but their eyes are completely locked on that dial gauge. If that needle jumps more than the allowed limit, it means the motor was sitting artificially flat. To relieve that tension, they actually have to insert ultra-thin sheets of metal, which are called shim plates, just to fill that tiny, microscopic gap.
Okay, we've verified the shaft alignment, checked our DBSE gap, and eliminated any soft foot tension. Now, it is time for the final verdict: tolerance and final verification.
This final verdict really just comes down to comparing two things: the raw, measured values our mill rates just found out in the field, against the strict safety limits dictated by the engineering specs. We call this concept tolerance. Basically, it's your maximum allowable error. If our measured deviation is within the tolerance limit, boom, the equipment passes inspection. But if it's outside the tolerance, no shortcuts. We have to go right back and adjust everything using those shim plates and jack bolts all over again.
What's super fascinating here is how the rules get dramatically stricter depending on the machine itself. As the equipment spins faster, the allowable tolerance shrinks. Take a look at this. Under 1,000 RPM, you get a maximum tolerance of 0.10 millimeters. But if it spins at over 5,000 RPM, that tolerance tightens to a microscopic 0.03 millimeters. The faster the machine runs, the more absolute perfection we demand from the installation. Which brings us to our final thought for today's explainer. If your equipment actually passes this rigorous tolerance test today, what invisible destructive forces have you just saved it from tomorrow? Mastering this seemingly simple alignment inspection sheet isn't just about ticking boxes for compliance. It is literally the ultimate key to mastering plant machinery longevity and preventing catastrophic failure before the power switch is even flipped. Thanks so much for joining me on this explainer, and as always, keep learning.